Imagine watching a single quantum particle slowly transform into a flowing fluid. This isn't science fiction. It's the remarkable finding we're about to explore, where environmental decoherence creates emergent hydrodynamic behavior from just 1 degree of freedom. Let's start with a fundamental puzzle that challenges our understanding of fluid dynamics. Building on this puzzle, the researchers ask whether environmental decoherence, rather than particle collisions, might be the missing ingredient. They propose that a single quantum particle, coupled to a thermal bath, could exhibit emergent hydrodynamic behavior. Now let's examine the elegant theoretical framework they constructed to test this hypothesis. The theoretical foundation rests on a single particle linearly coupled to a harmonic oscillator bath. This coupling creates both energy dissipation and spatial decoherence, fundamentally altering the particle's quantum coherence properties. This visualization captures the heart of the mechanism. As the environment interacts with the quantum particle, the off-diagonal elements of the density matrix in position space get systematically suppressed. The width along the off-diagonal direction shrinks over time, making the density matrix increasingly diagonal and classical-like. Here's where the authors make their crucial theoretical breakthrough. The mathematical approach is surprisingly systematic. By expressing the density matrix in center of mass and relative coordinates, they can exploit the decoherence-induced suppression of off-diagonal terms. This creates a controlled expansion where higher-order terms become increasingly negligible. This transformation is where the magic happens. The expansion coefficients naturally map onto familiar hydrodynamic quantities. The 0th order amplitude gives particle density, the 1st order phase gradient yields velocity, and the 2nd order amplitude coefficient becomes the stress tensor. Let's see what equations emerge from this quantum to classical transformation. The resulting equations are remarkably similar to Israel-Stewart transient hydrodynamics used in relativistic heavy ion physics. However, these emerge from pure quantum decoherence rather than particle collisions, with transport coefficients directly determined by the environmental coupling strength. What's particularly elegant is how the transport coefficients emerge directly from the quantum decoherence rate gamma. The relaxation time, viscosities, and even the equation of state are all determined by the fundamental quantum environment coupling, creating a complete hydrodynamic description. The authors provide compelling validation through both analytical solutions and mode analysis. The linear mode analysis reveals exactly what we'd expect from genuine hydrodynamics: one gapless diffusive mode that dominates at long wavelengths, plus additional gapped modes that become irrelevant at late times. This timescale separation is crucial for the hydrodynamic description to be valid. For the case without external potential, they obtained exact analytical solutions using the Klein-Kramers-Green's function. This provides a beautiful benchmark showing how the exact quantum evolution gradually approaches the Navier-Stokes constitutive relation at late times. The robustness of their approach is demonstrated through an independent derivation using Wigner function kinetic theory. Both methods yield identical hydrodynamic equations, confirming that the emergent fluid behavior is a fundamental consequence of decoherence, not an artifact of the mathematical approach. Let's consider what this breakthrough means and where it applies. The approach requires specific conditions for the Caldera-Leggett master equation to be valid. Importantly, this is an open system where momentum and energy are not conserved, leading to drag terms absent in isolated fluid systems. This work fundamentally changes how we think about the emergence of classical behavior. Instead of requiring many body interactions, hydrodynamics can emerge from environmental decoherence alone, providing a new lens for understanding small system phenomenology in contexts like heavy ion collisions. The authors outlined several exciting avenues for extending this framework. The framework opens rich possibilities for exploring non-Markovian environments, where anomalous diffusion might emerge, and practical applications to quarkonium evolution in quark-gluon plasma. Extensions to relativistic systems could connect this work to broader areas of theoretical physics. This remarkable work shows how environmental decoherence can transform a single quantum particle into an emergent fluid, fundamentally expanding our understanding of when and why hydrodynamic behavior appears in nature. To explore more cutting-edge research like this, visit emergentmind.com.